Hello, everyone. Today I'm presenting the paper Deterministic, Decremental SSSP, and Approximate min-cost flow in almost linear time. I'm Maximilian Probst Gutenberg from ETH Zurich, and this is joint work with Bernstein from Rutgers and Thatchaphol Saranurak from the University of Michigan. And this talk basically has two components or two parts. So the first one is a new data structure, the deterministic decremental single source shortest path data structure. And then the second part that I'm going to talk about in the first part. And then in the second part, I'm talking about a really cool application of this data structure, an application to approximate min-cost flow. Great. So let me get started on the data structure part. So the first thing I want to define properly, or at least informally, is what is a dynamic graph data structure. And for that, it's best to just start over with a static classic algorithm. So what is a static graph algorithm? In there, you normally have an input graph, and then you have some kind of problem. Let's say that you are given two fixed vertices S and T, and then the problem could be that you are interested in finding the shortest path from S to T. So you're given this input graph, you're given a problem, and now a static algorithm computes the shortest path from, or the distance from S to T, and it can output a witness, for example. Here, what you can see is that the shortest path is of length 3, and then the algorithm also gives a witness by just giving the shortest path between S and T. Okay. And opposed to this, a dynamic data structure for graphs does not have an fixed input graph, but instead you have an input graph that then undergoes updates. Here, for the sake of concreteness, let's fix edge deletions. And then as an update occurs to the graph, you want to immediately update the solution and adjust your output. So for example, for our problem, you're given this initial graph, right? Then you update the output or find the data structure finds the initial output, and then as the input graph undergoes the update, here an edge deletion, it has to update the output. So here it destroyed the deletion, destroyed the current witness path. So now it has to deliver a new witness, and here it can only prove that S and T are now at distance at most 4. And here's another example, just to clarify, right? Again, the witness is destroyed because an edge on the witness is deleted, and then your data structure would adjust and actually find a new shortest path and output the witness. And let me just clarify what we mean in which model we are working here. So when I say the input graph undergoes updates, then I mean that these updates, that the update sequence is not known to the dynamic data structure. It is created on the go by an adversary. And this means that as the adversary can create the updates on the go, it can basically use information from the witness, for example, extract information from the witness to make to design a particularly hard update to the input graph for this data structure. Exactly. Okay, and now that we are understanding the model, I want to give you the main result of this paper, which is a result for maintaining dynamic S to T shortest path. The main theorem of the paper is the following. So you're given an undirected weighted M edge graph. So a graph that initially has M edges, and that now undergoes a sequence of up to M edge deletions. And then, as before, we have fixed vertices S and T, and then there exists a deterministic data structure that maintains a 1 + epsilon approximate shortest path between S and T in total update time near linear in M. So what does that mean? You have fixing your vertices S and T, and then the graph that initially has M edges undergoes updates until the graph is empty, and after each update, the data structure adjusts the shortest path from S to T, and the total time spent over this entire update sequence of up to M edge deletions is near linear in M. Okay. And what this should be compared to is basically that before such a similar result was known in a weaker model only, that is in a model where the adversary had to design the update sequence before the algorithm started and not on the go. And we will see why this makes a huge difference, like why you really want the new theorem, which is also significantly harder to prove. Exactly. And for comparison, what we had before for such a deterministic data structure, before we had for sparse graphs, a data structure that ran in total time roughly m square root n. So we have a huge polynomial improvement actually in this update time. And you can see that there was a lot of work that was dedicated to improving this to finding this deterministic data structure. And now the problem is basically settled up to a subpolynomial factor. Okay. To understand the data structure a little bit better, I have some questions that you might have, and I'll answer them preemptively, basically. So you might ask, seeing this theorem, so what about insertions and deletions? So looking at the theorem, you see that the graph G undergoes m edge deletions, right? And you might ask, well, can I actually do a sequence of m edge insertions and deletions? Can I still get a really good total update time? And the answer is no. So there's conditional lower bounds that essentially show that for a mixed sequence of insertions and deletions, you do need at least mn time, which is off by an n factor of what we have. You might ask, well, what about the amortized versus worst case? So in particular, here you can see that if you really go over the entire sequence of m deletions, you will have an amortized update time for each update of subpolynomial in n. So very, very close to optimal. And you might ask, well, can we actually turn this into worst case update time? Can we have worst case subpolynomial in m update time per update? And it turns out that this is not possible. In fact, there might always be one update that takes all of m update time. You might also ask, noting that we are actually only maintaining a 1 plus epsilon approximate shortest path from S to T, can you actually maintain an exact shortest path between S and T? And the answer is, in this model, you cannot. There's, again, a conditional lower bound. And finally, you might ask, what about approximate SSSP? So can you just fix one source S and then maintain the distances to every vertex? And that is something that we can actually do. In fact, this is the data structure we really prove. So you can really maintain SSSP with 1 plus epsilon approximate shortest paths. But we will see later why I picked the ST shortest path problem, because that's really nice for the application. And then a final question is, you might also see that the graph here has to be undirected. What about directed ST shortest paths? And here, the picture is not complete so far. So there's still a lot of research on it, and there's some progress that essentially shows that you can get something non-trivial, but somehow this problem seems way harder. Okay. And now in the second part of the talk, I basically want to talk about the applications. So what can you do given such a decremental S to T shortest path data structure? And for this, I want to look at the ST max flow problem in undirected graphs. So you might recall that you are given a network here with capacities that I marked in red, and you have two dedicated vertices, and now you want to route as much flow as possible from S to T without violating the capacities. And here I'll just point out that the flow should have a direction. It could go either way in each edge, but I think here the direction is pretty clear. I didn't mark it, but I think you can hopefully see it from this example. And what I drew here is a maximum flow. So this is the maximum amount of flow you can push from S to T without violating the capacity constraints. Okay. So now that the problem is clear, let me show you a meta algorithm that by Karg and Kühnemann that is basically quite well known. It's the multiplicative weight update framework, where you do the following. So you're given your graph with your capacities, and now you can introduce a weight function. And initially, you just let the weights be 1 everywhere, and you initialize your flow to be 0. And now in line 3, you see that there's a loop starting, a while loop starting, and it runs until you find a near optimal flow. And as long as you don't have that flow, what you essentially do is you pick the shortest path from S to T. This can be approximate according to that weight metric. So here the green weights you can see, we have unit weight, so it's just the one of short with the fewest edges. Then on this shortest path, the current shortest path, you find the edge that has the minimum capacity. So here you can see the first edge has capacity 10, the second has capacity 4, the third has capacity 5. So the min capacity is 4. And now you're augmenting along that shortest path, and you want to push min capacity, so 4 units of flow, scaled down by a normalizing factor. So here the normalizing factor n I set to be 2, so I'm pushing 2 units of flow. And once you push that flow, you're updating the weights, and essentially each weight on each goes for each edge that received new flow, the weight goes up according to the flow. So here you can see it's actually multiplicatively going up, and you scale as much by C. Here you can see in line 8 that the weight adjusts to be the original weight times 1 plus epsilon, and here the min capacity, so the capacity, the amount of flow you basically scaled by pushed without the normalization factor, divided by your capacity. And if you do this a couple of times until you reach the optimum, or up to 1 minus epsilon of the optimum, you essentially get a shortest path, get a maximum, ST maximum flow, approximately. And what you can see is that in line 4, you're basically always just asking for the shortest S to T path, approximately, right? And since the weights go up, weights going up, you can actually simulate by edge deletions, because for each edge that you have initially, you can insert edges of weight 1 plus epsilon to the I for every I, and then just delete all the edges that have weight smaller than the current weight. And this gives you a 1 plus epsilon approximation. So given all of this, we get the following result. Given an undirected capacitated graph G, vertices S and T, we can find a 1 minus epsilon approximate max flow in near linear time. And I just want to point out here, after theorem, I wrote advanced MWU. And the reason is that if the graph has no capacities, then the original framework by Garg and Kahneman would work very nicely, but actually to get capacitated graphs right, you have to introduce some randomization and you actually have to do something quite non-trivial, both on the data structure and in the MWU, but this should be the basic intuition, and then you can also handle capacitated graphs at no further cost. Let me briefly remark that this result has previously, I mean, this is certainly one of the easier ways to get this result, and also a very nice combinatorial approach, given that you consider MWU to be somewhat combinatorial. But this result has basically been known before. I think I have the reference popping up in a second. But what we can actually do is we can also deal not only with edge capacitated graphs, but the MWU is actually quite flexible. So now you can also have vertex capacities, and you can also compute the min cost flow. So you can have a cost function over all the edges, and then you're minimizing the cost of the maximum flow that you're pushing. Exactly. Previously, we only knew how to do edge capacitated graphs. This was known by Sherman, KLOS 14, and then by Peng, who actually improved it to be M polylog n time. But as I said, vertex capacities or a cost function is something that they cannot handle. From our new results, so basically from the vertex capacities and the min cost flow result, we also get some very nice new near linear time algorithms by reduction. We get an approximate sparsest vertex cut algorithm. We get an algorithm for the weighted p-norm flow. I'll not go too deep into this. And you can get vertex separators and tree-width decompositions, all to a polylogarithmic approximation. These are quite cool applications, I think. And you basically get them by standard reductions once you have our vertex capacitated or min cost max flow. I also want to point out two limitations. The first one is all the algorithms you've seen are low accuracy. This means the runtime dependency in our epsilon is very bad. It's polynomial or worse. And yeah, essentially you want the epsilon in the 1 minus epsilon approximate shortest max flow or shortest path. You want it to be a constant like 1/10 or something like that, but not a polynomial like 1/n. And another limitation is that currently the framework is really tailored to ST shortest path, ST max flow problems, and for channel demands, it does not generalize seamlessly. This is something that we hope future work can maybe address, but we're not quite sure. Okay. And finally, just to conclude, what you've seen in this talk is, I hopefully convinced you that there's a powerful new dynamic graph data structure that maintains shortest paths in the graphs undergoing edge deletions. And this gives a conceptually very simple algorithm for approximate max flow in undirected graphs. And you can handle new variations of the problem. And then basically there is like an open question or like work in progress, and that asks, can we maybe use this powerful new dynamic graph data structure also to obtain faster flow algorithms for other problems, for variations. For example, recently, this data structure has also found application for in computing Gomery-Hu trees very quickly. So we hope that our data structure finds many applications. Thank you very much for your time.